Hello, hello guys. Good morning. Good morning to all of you. Can you hear me? Can you hear me? Today we'll be discussing mathematical tools of quantum mechanics. So this may take a couple of lectures, and this is the first part. So before I start, let me know if everything is all right. So mathematical tools of quantum mechanics. These tools are very essential in understanding the upcoming topics which we'll be dealing with in the upcoming discussion of quantum mechanics. You know, the Schrodinger equation is the basis of quantum mechanics. The Schrodinger equation is one of the cornerstone of the theory of quantum mechanics. It has the structure of a linear equation. Schrodinger equation is a linear equation. There is no higher power. Like d square psi by dx square. You see, only power is 1. On the other side, v of x into psi, e psi. So you can see this is a linear equation. The formalism of quantum mechanics. Good morning, Harry. Formalism of quantum mechanics deal with operators that are linear. So you will be seeing many operators like momentum operator, energy operators, and many other types of operators which are linear in nature, and wave function that belong to abstract Hilbert space. So we'll define this Hilbert space in few moments. The mathematical properties and structure of Hilbert spaces are essential for proper understanding of formalism of quantum mechanics. So this basic mathematical tools which we will be discussing in the next part of this Hilbert space. We are going to review briefly the properties of Hilbert space. We'll talk about, and those of linear operators. Then we'll consider the bra-ket notation. Bra-ket notation is very essential in understanding many things in quantum mechanics. Quantum mechanics, basically formulated in two different ways. One is given by Schrodinger, another one is given by Heisenberg. The approach given by Schrodinger is known as wave mechanics. Okay? Quantum mechanical approach. If we classify this is very important. We have two approaches. One is the wave mechanics approach, by taking wave function and doing things. Another one is Heisenberg's model, matrix methods. So using any operator and expressing them in the form of matrix, we have another approach. So we'll also learn about this. Most of the time we use this wave mechanics, but matrix mechanics is equally important. So these are the two representations, wave mechanics and matrix mechanics, for the general formulation of quantum mechanics in continuous and discrete basis system. So we'll also talk about this basis. What is this continuous basis, discrete basis and all. So for this we have to study kets, bras, brackets, operators in different basis, maybe in discrete basis or it may be in a continuous basis. Okay. Good morning, Murli. Now, as I told you, we have to study Hilbert space. So before directly jump into Hilbert space, we need to have the idea of the linear vector space. So Hilbert space is one space which has the property common to the linear vector space. Linear vector space, you can imagine that it is a sub part of the Hilbert space. So what is this linear vector space? You all know about it. You have read it in mathematics. So you see, a linear vector space consists of two set of elements and two algebraic rules. One is this addition, vector addition, and scalar multiplication. These two are the rules: vector addition and scalar multiplication. So here we define a set of vectors like psi, phi, chi, and so on, and we also define a set of scalars a, b, c, and all. So it is subjected to two different rules. One is the vector addition rule, another one is the scalar multiplication. So let's talk about this vector addition rule. So it has certain properties and a structure of an abelian group. So let's say if psi and phi are vectors of a space, then their sum psi plus phi is also a vector of the same space. So it is like, you can imagine the three-dimensional Euclidean space. So if psi is one vector, let's say 2i plus 3j cap, phi is another vector 5i minus 7j cap, then their sum will also be a vector of the same Euclidean space, no? So you can imagine it in this way. Commutativity, psi plus phi is equals to phi plus i. This property is known as commutativity. Psi plus phi is equals to phi plus psi. Associativity, psi plus phi plus psi, you can see a bracket is here. So this bracket can be transferred, equals to psi plus phi plus chi. So this property is known as the associativity. Now this is very important: existence of a zero or a neutral vector. Zero vector will be denoted by this, like O. It is different. This is 0, and when we are writing zero vector, you can write it in this way, little bit big and little bit tilted. Okay, just to differentiate. Existence of a zero or neutral vector: for each vector psi, there must exist a zero vector O such that O plus psi is equals to psi plus O is equals to psi. So this is very important property. Next property is the existence of a symmetric or inverse vector. So each vector psi must have a symmetric vector minus psi such that psi plus of minus psi is equals to minus psi plus of psi is equals to 0. So these are 5 rules which comes under this vector addition. What about the scalar multiplication rule? Look, these are just for your reference. Okay, it may be useful for making a base in mathematics. You have already read it. I have just gathered it at one place. Multiplication rule: multiplication of vectors by scalars. You know, vectors we have psi, phi, and chi. Multiplying them with scalars like a, b, c. The scalar may be real or maybe some complex numbers, I cap, complex numbers like I, 2i, 3i, and so on. So it has got this property: the product of a scalar with a vector gives another vector. Simple thing, like if you have a vector, let's say 2i cap minus 3j cap. So if you multiply with a scalar, let's say we multiply with 2, it will become 4i cap minus 6j cap. So that is also a vector. So that is why product of a scalar with a vector is another vector. In general, if psi and phi are two vectors of the space, any linear combination like a psi plus b phi, this is known as linear combination of psi and phi. So then it will also be a vector of the space. You can, if you imagine the Euclidean space, three-dimensional Euclidean space that we generally use, that will give you, that is a linear vector space. So if you take the analogy or example from that space, then things will be pretty much clear to you. So any linear combination of these two vectors psi and phi is also a vector of the same space. Distributivity with respect to addition. So if you multiply a scalar onto the addition of two vectors, you get, so you can see the product is distributed a psi plus a phi, a plus b psi, so a psi plus b psi. Associativity with respect to multiplication of a scalar, a b psi is equals to a b psi. So you have to be familiar with this kind of term. What do you mean by associativity, distributivity? For each element psi, there must exist a unitary scalar I and a zero scalar O such that I psi is equals to psi I is equals to psi. So it is similar to the identity matrix, isn't it? And this is like the null matrix, 0 psi, psi 0 is equals to 0. So these are some properties of the linear vector space. So if these properties of vector addition and scalar multiplication is followed, then we can say that the corresponding space is a linear vector space. Now what about the Hilbert space? So in a Hilbert space, you can see it is denoted by this curly H. Hilbert space, curly H. I will share the PDF, you don't need to write. So Hilbert space consists of set of vectors as before, psi, phi, chi, and here also we have a set of scalars a, b, c, which satisfy the following four properties. Out of these four properties, the first property, H is a linear space, means whatever properties we have discussed in the linear vector space, that will also be there in the Hilbert space. Okay, this is the first one, that H is the Hilbert space is a linear vector space. And what are the properties of linear vector space we have already considered in the previous section. B, H has a defined scalar product and it is strictly positive. So it will have a defined scalar product. So now understanding scalar product is very crucial. Try to understand. For the time being, we are doing it in a normal way, then later on we will convert this scalar product into the bracket notation formalism. So scalar product of any element psi is what? It is a vector with another element phi, that is another vector. So scalar product of psi and phi in general is a complex number and it is given by psi phi. The order matters a lot. You cannot write phi psi, psi phi and phi psi are not same. Okay. So scalar product of psi with phi is given by psi phi with the first bracket, where psi phi is a complex number in general. Watch out from the order. Since the scalar product is a complex number, the quantity psi phi is not generally equals to phi psi. How they are related? Psi phi is equals to psi star phi. So whenever you do the scalar product, you take the complex conjugate of the first vector. Psi is located at the first place, so you take psi star, then you keep phi. Later on we'll show you this is actually this thing, psi phi in bracket notation, because it is a bra, that is why we give star to bra and ket remains intact. Okay, we will talk about it later. For the time being, you know this. Phi psi will be phi star psi in a similar manner. So psi phi and phi psi are not same. The scalar product satisfies the following property. Now this is important. Scalar product of psi and phi is equals to complex conjugate of the phi with psi. So you see psi phi will become psi star phi, and psi star phi is nothing but phi psi star. Okay. So psi phi is equals to phi psi star. This is the first property. Is there any question till now? Tell me. Or any difficulty in understanding? You can do it in this way, psi phi. From the definition, you know, it is psi star phi. Okay. And what about phi psi star? Phi psi star means phi star psi. Now star. So when you take complex quantity, it applies from the right. So psi star phi star star means phi. So that is why psi phi is equals to phi psi star. I hope this is all clear. The scalar product of phi with psi is linear with respect to the second factor. Linear with respect to the second factor means whatever terms will be here. With respect to that, it is linear. So a psi 1 plus b psi 2. So you see this a is scalar is coming out. Phi psi 1 plus b phi psi 2. Antilinear with respect to the first factor. So you can see a phi 1 plus b phi 2 psi. So antilinear, you see here it was purely a and b, but here it is, you see, a star phi 1 psi plus b star phi 2 psi, because this is at the first position, and actually it is followed from here, you see, scalar product. So when it is coming out of this product, it will come out as star. So that is why we have a star here, b star here. Look, when you will be practicing problem, then these things will be very common to you. Okay, if you are learning it for the first time, it may appear to be a little bit confusing, but once we start solving problem, these things will automatically come. A phi 1 plus b phi 2 psi, this is done. The scalar product of vector psi with itself is a positive real number. The scalar product with itself, so it is, you see, psi star psi. Psi star psi means mod psi square, that is greater than or equals to 0. So it gives you a positive real number, scalar product with itself, where the equality holds only for if psi is a null vector. Now the third property, second property is like it has a definite scalar product that is strictly positive, and the third property of the Hilbert space is separable. They are purely mathematical. So you see, there exists a Cauchy sequence psi n belongs to H, n may be 1, 2, 3. So you can see it is a set of vectors such that for every psi of H, epsilon greater than 0, means between two, you can always find one. Okay, between two vectors, you always find one vector which satisfy this property. There exists at least one psi n of the sequence for which psi minus psi n mod less than epsilon. Multiplication of scalar with vector gives scalar. No, that will give you vector, no? Multiplication of scalar, let's say 2, with vector, let's say 5 I cap plus 7 j cap. So what should it give you? 10 I cap plus 14 j cap. So this is also a vector, no? This is a vector, say scalar. Clear, Harry? Murli, what are you asking? What you mean by the word key, sir? Which one? Can you rewrite, Murli? H is complete. Every Cauchy sequence psi n belongs to H converges to an element of H. That is, for any psi n with the relation limit nm tends to infinity, psi n minus psi m equals to 0. Defines a unique limit of psi of H such that limit n tends to infinity, psi minus psi n equals to 0. So these are not so much useful. Just for the sake of completeness, we have just told you the 4 properties. Mainly this third property is important, which we will also deal with in the bracket notation. When you teach, you are using the word T-chi. T-chi? What is T-chi? Oh, ठीक है means oh my god, ठीक है means is it okay? Yeah, instead of saying is it okay, ठीक है is a like concise form. Okay, let's move on to this dimension and basis of a vector space. Let's say we have n set of vectors. A set of n vectors. Let's say we have phi 1, phi 2, phi 3 and so on up to phi n. So this set of n vectors is said to be linearly independent. When we call this set of vectors linearly independent, under one condition, if and only if the solution of the equation, let's say ai phi I, if you sum it over the limit I is equals to 1 to n equals to 0. So this is an equation, and the only solution possible to this equation is that all these coefficients a1, a2, a3, a4 and so on all are 0. That is the only solution exists. If that is so, then you can say that phi 1, phi 2, phi 3, these are a linearly independent set of vectors. So this thing you must have read in mathematics, isn't it? But you see here how many scalars are there? a1, a2, a3 up to an. So n number of scalars are there, right? Now let's say some of them are linearly dependent, some of them are linearly independent. Then what will be there? But if there exists a set of scalars which are not all 0. So from the linearly independent condition, these scalars, all of them must be 0. But if you see that there are some scalars which are not all 0, so that one of the vectors, say phi n, can be expressed as a linear combination of the others, linear combination of the others in the following way. Let's say if you have phi n, it is one of the vectors which you have taken. If you can write them as a linear combination of the other vectors, let's say I is equals to 1 to n minus 1. N minus 1 ai phi I plus I is equals to n plus 1 to n ai phi I. Acha, let's say this is not capital N, this is small n. So somewhere between phi 1 and phi n, we have this phi small n. See, midway maybe, some other place, not this capital N. So you take a sum from I equals to 1 to n minus 1, okay, then phi n comes, then next n plus 1 to n. So if we can represent it in this way, then we can say that that set is a linearly dependent set. So if this is possible, if this happen, we can say that the set phi I. So this represents the whole set phi 1, phi 2, phi 3 and up to phi 1. This set is said to be linearly dependent. Is it clear? This linearly dependent thing. For both n and n start with 1 to 3. No, it is not like that. It is like, you can imagine it in this way. We have this vectors phi 1, phi 2, phi 3, phi n minus 1, phi n, phi n plus 1, so on up to phi capital N. So in this way there are n number of vectors. So if you can write one of these vectors in terms of the others, okay, then it is said linearly dependent. And if they are not expressible, let's say phi 3 we cannot express in terms of the others. Let's say for an example, I am taking the Euclidean space. So the unit vectors I cap, j cap, k cap, they are linearly independent, right? All of them are linearly independent. So can you write I cap or j cap in terms of the other two? Let's say I cap, can we express I cap in terms of j cap and k cap? No. Can you express j cap in terms of I cap and k cap? No, because they are linearly independent. On the other hand, if I take, let's say 2 I cap plus 3 j cap plus 5 k cap, so this is a linearly dependent, no? Because we can express it in terms of this I cap, j cap, k cap. Now dimension. What is dimension? Dimension is the number of maximum linearly independent vectors a space can have. Okay, maximum number of linearly independent vectors a space can have. So for the three-dimensional Euclidean space, what should be the dimension? So I have already told you it is 3 dimension, but why it is 3? Because it has the maximum 3 linearly independent vectors I cap, j cap, k cap. So the dimension of this vector space is 3, isn't it? So dimension refers to the maximum number of linearly independent vectors. The dimension of a vector space is given by the maximum number of linearly independent vectors of the space. let's say for a space, if the maximum number of linearly independent vectors of a space is n, let's say phi 1, phi 2, phi 3 to phi n. So these are all linearly independent vectors. If we consider, then you can say that the space is n dimensional. If the maximum number of independent vector of a space is n, then that space is said to be n dimensional. With the help of this n vectors, we can represent any vector of that space. In this space, any vector psi can be expressed as the linear combination of the n linearly independent vectors. How? Let's say psi, we can express it as a linear combination of these vectors. So ai phi I, linear combination means you have to take the limit from I equals to 1 to capital A. So dimension is the number of linearly independent vectors. That is the dimension. What is basis? Basis is known, those vectors, the set of vectors are known as the basis. So for Euclidean space, what is the dimension? Dimension is 3, because 3 linearly independent vectors are there, I cap, j cap, k cap. And what are the basis? Basis vectors are I cap, j cap and k cap. Simple. Let's talk about basis. What is basis? The basis of a vector space consists of a set of maximum possible, it is maximum possible number of linearly independent vectors. Linearly independent vectors. Belonging to that space. As simple as that. For Euclidean space, I cap, j cap, k cap, these are the basis vectors. So what we do, let's say we have these basis vectors, the set of vectors, let's not take an example. Let's say phi 1, phi 2, phi 3 and up to phi n are there. So we represent it in short as within the second bracket phi I. In this way we represent this set of vectors. So this phi I, this is called the basis of the vector space. This set of vectors is known as the basis of the vector space. Now you see these basis vectors, let's say phi I, they can be orthonormal. The basis vectors phi I, they can be orthonormal. What is the definition of orthonormal? So the basis vectors will be called orthonormal basis if it contains orthonormal vectors, isn't it? So condition for being orthonormal, what is the condition? Condition for being orthonormal set, orthonormal basis. So condition for being orthonormal, let's say we have two vectors phi I, another one is phi j. The scalar product of phi I and phi j, it should be delta ij. Delta ij is the Kronecker delta. It has a value of 1 if I is equals to j. It has a value of 0 if I not equals to j. So this is the condition for orthonormality. Now this basis vector, we call it orthonormal under this condition if it follows. Now another thing is there, when we call these basis vectors to be complete. The basis is said to be complete when this basis vector spans the whole space. Spanning the whole space means we can represent any vector in terms of the basis vector. If you take up the example of Euclidean space, whatever vector I give you, you will be able to represent that in terms of the basis vectors I cap, j cap, k cap. If I give you 17 I cap plus 23 j cap plus 15 k cap, so you are representing it in terms of I cap, j cap and k cap, right? Let's say I am giving you 5 I cap minus 3 j cap. So you can represent it 5 I cap minus 3 j cap plus 0 k cap. So we are representing it in terms of the linearly independent vectors. So that is why I cap, j cap, k cap, this set of vectors which forms the basis is said to be complete. The basis is said to be complete if it spans the whole space. If it spans the whole space. So you do not need any additional vector to represent any vector in that space. Only the basis vectors are sufficient. And the expansion coefficient which we have seen here also, AI, A1, A2, A3, they are called the expansion coefficient. The coefficient AI is called the components of the vector psi in the basis. I hope everything is all right. सब ठीक है? Is it clear, guys, or any question you have? You can let me know. Another thing you can write here, each component is given by the scalar product of psi with the corresponding base vector. Let's say if you want to represent, look, psi we have represented by the linear combination of the other vectors. Okay, let's say AI phi I sum over I. So if you want to get any component, let's say AI or AJ, then what you gonna do? If you want to get AJ, then you have to take the scalar product of psi with the corresponding base vector. Okay, what is the corresponding base vector of AJ? It is phi j. So you have to take the scalar product of that corresponding base vector with psi. So it is like that. So these are very fundamental ideas I think you should know about. Now some example of linear vector space. So we are giving here two linear spaces that are Hilbert spaces, one having a finite or discrete set of base vectors. So that example of Euclidean vector space we are already giving it from the very beginning. So you know it has three base vectors I cap, j cap, k cap. So this is finite, or it may be infinite or continuous basis. So for finite basis you can count the number of vectors, basis vectors, like I cap, j cap, k cap, you can count, it is 3. But for other vectors that is infinite or continuous basis. So mainly the first one is generally used. First one is the 3-dimensional Euclidean vector space. The basis of this vector consists of 3 linearly independent vectors I cap, j cap, k cap. Any vector of the Euclidean space can be written in terms of these vectors, because this will be I cap, j cap, k cap. Any vector you can represent in terms of I cap, j cap, k cap, where A1, A2, A3, these are the components of A in this basis. Each component you can determine by taking the scalar product of A with that corresponding base vector. So if you want to, let's say, calculate A1, what you gonna do? You're gonna take the dot product of A with I cap. So I cap dot A, A2 is j cap dot A, A3 is k cap dot A. Note the scalar product in the Euclidean space is real and hence symmetric. Norm on this space is usually the length. Norm means, let's say, in 3-dimensional space, if you want to take the distance between these two. So this is called a norm, and it will come out to be positive because this represents length in the Euclidean space. Note also that whenever a1 I cap, a2 j cap, a3 k cap equals to 0, we have a1, a2, a3 equals to 0, because their I cap, j cap, k cap are linearly independent vectors. So the coefficient a1, a2, a3 must be 0, and that none of the unit vectors I cap, j cap, k cap can be expressed as a linear combination of the other two. You cannot express I cap in terms of j cap or k cap, right? Or you cannot express j cap in terms of I cap, k cap. So we have already told you. Second example, which involves the continuous basis, is the entire complex function psi x. Dimension of this space is infinite because it has infinite number of linearly independent basis vectors. Let's talk about this now. Square integrable function. We have already give you a hint while discussing the normalization. So square integrable. Let's say we have two functions. So what will be the scalar product? The scalar product of two functions. Let's say psi x and phi x. So the scalar product is given by, how do we write psi phi? So this is in terms of integration, it is written as psi star of x, phi of x dx. Let's say this is equation number 1. Now this integral, that is a scalar product, if this integral diverges, then you can say that this scalar product does not exist. If this integral diverges, the scalar product does not exist. Scalar product does not exist. Okay. So we have to select this function in such a way that the scalar product remains finite, so that this integral remains finite. So as a result, if we want the function space to possess a scalar product, we must select only those functions for which the scalar product psi phi is finite. Okay. Now in particular, a function, let's say psi of x, it is said to be square integrable, if the scalar product converges or finite with itself. Here we have taken a scalar product of psi with phi. So if you take the scalar product of psi with itself, means psi, then, and if that integral converges or remains finite, then you can say that is square integrable. So in particular, a function psi x is said to be square integrable if the scalar product of psi with itself So what does it mean? Previously it was psi with phi, now it is with itself. So psi psi, so this will be psi star x psi x dx. What does it mean? Mod psi of x whole square dx. So where have you seen this? In the discussion of normalization. Okay, now you have seen it in the discussion of normalization. So if this is finite, we can say that the said function is square integrable. Is it clear? Here you can add a note that any linear combination of the square integrable function is also square integrable. Any linear combination of square integrable function is also square integrable. Now we have talked about wave function. So wave function must satisfy this property, means the wave function psi of x, it must be square integrable. The best example of the square integrable function is the wave function. If the wave function is not square integrable, then that is not an allowed wave function. Okay. So a good example of square integrable function, square integrable function is the wave function. Wave function must be square integrable. So wave function, how do we represent it? We represent in 3 dimensions. Let's say psi of, we previously represented by psi of xt, but for 3 dimensions it will be psi of rt. So psi of rt, this represents probability amplitude. So psi of rt mod square d cube r. What does d cube r represent? D cube r represents the volume. Okay, so because we are considering 3 dimension, so we cannot say it is dx. Dx is for 1 dimension. When we are using d cube, means we are talking about some infinitesimal volume. So what does this thing gives you? It gives you the probability of finding the particle, of finding at time t. Probability to find the particle at time t in a volume d cube r, and this approach or this convention was given by Born approximation, right? Born's probabilistic interpretation. We can say that psi of rt mod square dq bar represents the probability of finding the particle at time t in a volume dq bar. It is given by the scientist Born. So it's Born's probabilistic interpretation. So if this is the probability to find the particle in some volume V. So if you scan over the whole space, we'll definitely get the particle. The particle will be somewhere in the space, right? So if you integrate it over the whole space, it should give you a certain event 1, because the particle must be found out. So that is why the probability to find out the particle, somewhere in space must then be equal to 1. So what does it mean? Mod of psi of RT whole square d cube r. So you see, this is in 3 dimension. dq bar consists of dx, dy, dz, right? So we can also break it up. We scan from minus infinity to plus infinity of the x dimension, minus infinity to plus infinity dy, minus infinity to plus infinity dz. So this whole thing is precisely dq bar. Look, if we write dz, then this will not be a good thing. You can write psi of RT square dz equals to 1. So this is equation number 3. So first we will evaluate dz, then whatever you will get in, you will integrate on dy, then you will integrate on dx, and in this way you can integrate the whole. So you see, this value of this integration is 1. It means it is finite. So what you can conclude? We can conclude that the wave function is square integrable. And the wave function is square integrable. And the wave function which are square integrable, they follow the normalization condition. This is also very good interpretation. Note that wave functions satisfying equation 3 are said to be normalized or square integrable. So any wave function which will not be square integrable, that is not a physically acceptable wave function. So if you see, after taking this integral, you get a diverging result, then you can say that this wave function is not a valid wave function. So that also you can write, any wave function which is not square integrable has no physical meaning in quantum mechanics. Okay guys, is it clear or is it getting heavy? Tell me quickly. Everything all right? Why are you so silent today? Harry, Karthik, Murli, going everything right? Or is it going over the head? Simple thing, I think you should be able to understand. Clear, na? Okay, let us now go for this Dirac notation. This is very important. Dirac notation. So look, any vector psi. So as per this Dirac notation, what he did, any vector psi, let's say, which is square integrable. Square integrable, that is the prerequisite of being qualified as a wave function. If you are calling something a wave function, it must be square integrable. That is a prerequisite. Any vector psi which is square integrable, what Dirac did, he represented it by some ket which is square integrable is represented by ket vector. Ket vector. Ket looks like this. How will you read it? You will read it as ket psi. Ket psi. And its conjugate, by a bra vector. Bra is looking like this. This will be read as bra psi. This is ket psi, you see, towards right, and this arrow towards left. This is bra psi. Now the scalar product. How do you represent the scalar product? The scalar product, let's say previously it was phi psi, is, and this notation is not known as bra-ket notation, because you see this is bra and then ket, that is why it is called bra-ket notation. Scalar product psi phi is represented in bracket notation as, how will you represent it? Psi psi in this way. Clear, sir, but not feel interested. Yes, this is a little bit boring part, but this is very necessary. You cannot ignore it. This is a basic thing, okay? You must understand. You will enjoy it eventually. If you are learning it for the first time, it may finding a little bit odd, but okay. It is like that bitter medicine which gives very good benefits. Now try to understand this. Dirac notation is very important. So any vector psi, you can represent it by ket psi. If you want to represent psi star, you can represent it by bra psi. Scalar product of phi psi in bracket notation, we represent it by this symbol, phi psi. What is phi psi? It is nothing but psi star of RT, phi of RT d cube R. So this is in 3 dimension. If you write this same thing in 1 dimension, it will be phi star of x, psi of x dx. Now there are some properties of this bra and kets. Let's say properties of bras, kets and brackets. Let's say if you have ket psi, you are taking the complex conjugate, you will get bra psi. Let's say a scalar with ket psi. If you take the complex conjugate, what should you get? A star, and this will become bra psi. Simple thing. Let's say within the ket a psi is there. What do you write? A psi. So the first property, which one? Yeah, ket psi star is equals to bra psi. When taking complex conjugate should not be transformed to ket. Complex conjugate of a ket gives you a bra. Okay, na? You took complex conjugate of ket psi, that gives you bra psi. Here A is a scalar, so A star, and complex conjugate of ket psi is bra psi. Here A psi is equals to A psi, because from ket, when it is coming out of the ket, then there will be no complex conjugate. When it is from the bra, it will come with a star. Let's say, you see, A was inside the ket, so there is no complex conjugate here. But let's say A psi, if you have like this, so A is coming out of the bra, so A will have star. So ordering is important. You see, ordering is important. Psi phi, scalar product of psi phi, let's say psi phi is not equals to phi psi. Rather, phi psi star, this is equals to psi phi. So ordering is important. You can see psi phi scalar product star. So what is psi phi? Phi psi, it is phi star RT. Try to understand it. Psi of RT. Look, these things are complex when you are learning it from the first time. That is why I am going a little bit slowly. But once you understand, you will be overpowered. So we have written this scalar product. For the scalar product, you know, the first term it comes in complex conjugate, then the second term remains intact, and this in 3 dimension it is d cube, or in 1 dimension it is dx. Now star. So what will it become? This complex conjugate will be applied from the later portion. So this one will come first with star, psi star RT, then phi star star, so it is phi of RT, d cube R. So what is this? This is nothing but psi phi. Look, these two will be equal when, under what condition these two may be equal? Look, if psi star is equals to psi, phi star is equals to phi, means if they are real, then this equality will hold. When phi and psi are real, then psi phi, scalar product of psi phi is equals to scalar product of phi psi. Okay. Let's go for some other such operations. Let's say I'm giving you psi, bra psi, then a1 psi 1 plus a2 psi 2. What are you going to write? A1 is not under the bra, it is on the ket side. So A1 will come out as A1, then psi 1 plus A2 is also inside the ket, so psi 2, as simple as that. Let's take another one, A1 phi 1 plus A2 phi 2 psi. So A1, you see, it is in the bra, so it will come out as A1 star, phi 1 psi plus A2 star phi 2 psi. This properties will be very much useful while solving problems. Later on we will be doing advanced problems, then these simple concepts will be very much essential. These are like you are gathering the weapon to fight. Say A1 phi 1 plus A2 phi 2, B1 psi 1 plus B2 psi 2. What you gonna write? You just write before me. This will be A1 star B1 psi 1, sorry, phi 1 psi 1. Plus A1 star B2 phi 1 psi 2 plus A2 star B1. You can see we are taking the complex conjugate only for those terms which is coming out of the bra, phi 2 psi 1, and the last term will be A2 star B2 phi 2 psi 2. I hope this is clear. Now with this bracket notation we can simplify many expressions. Let's say if you are considering the norm means if you have a ket psi, this psi this is called the norm or normalization. This is real and positive for any vector in the Hilbert space. Means if you consider any wave function, then if you take the norm, you will get a positive real number. And it will be 0 only when psi is 0. So if you get, let's say, this is a very important thing, if the state psi, ket psi, let's say it is normalized, then what you can write? Then we can write that the scalar product with itself, that is the norm, is 1. Okay, so in a very precise way we can write with the help of bracket notation. Now some other less important properties are there, like squads inequality. Squads inequality. You can just remember them or read them out. Squads inequality, it is given by this inequality. Let's say scalar product of psi phi, you take mod square, this is less than psi psi phi phi. This is known as squads inequality. Then there is another triangular inequality. Triangular inequality. So we are just representing these inequalities in terms of the bracket notation. So square root of psi plus phi, psi plus phi is less equal to psi psi plus phi phi. So this triangular inequality you must have read, that is the length of the third side is less equal to the combined length of the other two sides of a triangle. So that is the triangular inequality, and this triangular inequality is represented in the bracket notation in this way. Now orthogonal sets. Orthogonal sets. So let's say we have a set of vectors which are orthogonal. So we can also represent it in terms of the bracket notation. Let's say we have two kets, psi ket and phi ket. They are said to be orthogonal. How to check whether they are orthogonal or not? If they have a vanishing scalar product. So if you get this product, let's say psi phi, this is scalar product of psi phi. If it is 0, then you can say that these two set of vectors are orthogonal set of vectors. Now there is a basic difference between orthogonal and orthonormal. They are closely related. What is the difference between orthogonal sets and orthonormal sets? Orthonormal means orthogonal plus normalized. Remember this one. So here also two kets, let's say psi and phi, are said to be orthonormal if, first condition, they are orthogonal. If they are orthogonal to each other and they are normalized, and if each one of them has a unit norm. Unit norm means the scalar product is 1 with itself. So the first criteria is they must be orthogonal, means psi phi should be 0. They are they having unit norm, means psi is equals to 1 and phi equals to 1. So this difference must be kept in mind the difference between orthogonal set and orthonormal set. Now there are some forbidden quantities which you should remember. So you cannot write everything, whatever comes into your mind, you cannot write arbitrarily in the bracket notation. There are some forbidden quantities as well. What are those forbidden quantities? Look, if we have this ket psi, ket phi, then we could write the scalar product of psi phi or phi psi, whatever you want to write. But a product of the type, let's say ket and ket psi, this is not allowed. Okay, na? Not allowed. Or psi phi, this is also forbidden. These are nonsensical. That does not mean nonsensical. They do not give any sense. So it may happen that we have two basis vectors, one belong to some space, another belong to another space. Then their product, if you want to write it psi phi, this is not written in this way. Rather, the allowed portion is written in this way. If you want to write it in terms of this, you have to write it by this. This is called outer product. We will talk about it later on also. So this represents a tensor product of psi and phi. So this only this type of cases are meaningful, not this or this. So I hope you have got pretty much idea about this thing. Let's go for some problem. Okay, too many blank spaces is Let's consider this problem. Now I think you can easily do these problems. Ket psi is given. Ket psi, you remember, ket psi is a column vector. Ket psi or ket phi is a column vector. When you consider bra, then that will be a row vector. So find the bra psi. Let's calculate the first one, bra psi. Ket psi is given to you. You know, bra phi is nothing but the complex conjugate of the ket psi. So complex conjugate means you have to write it in this way: 2 plus I, 2 plus 3i. Okay. Evaluate the scalar product phi psi. Phi psi. So phi means, bra phi means it's a row vector. 2i 2 plus 3i. Ket psi, it will remain as it is, minus 3i 2 plus I 4. So that just take the scalar product, sorry, matrix multiplication, 2 into minus 3i, so minus 6i, 2 into minus 3i plus I into 2 plus I plus 4 into 2 plus 3i. So if you calculate this, what are you gonna get? Minus 6i plus 2i, 4i plus 12i, plus 8i. What about the scalar part? I square minus 1, so 7. So 7 plus 8i. This is the scalar product. Examine why the product psi pi, phi psi do not make sense. We have already talked about it, that this scalar product phi psi in this way and phi psi in this way, they do not make any sense. You see, if you want to take this product, so you know ket psi, it is a column vector, ket phi, it is a column vector. So if you have two column matrices, column vectors or column matrix, two column matrices cannot be multiplied, you know it from matrix mechanics. Okay, so in linear algebra we know that the product of two column matrices, you know there is certain rules to take matrix product. The product of two matrices, column matrices to be precise, two column matrices cannot be performed, cannot be performed. In a similar way, if you consider, let us say, phi psi, so this is a row vector, this is also a row matrix or row vector, so this product is also not possible. So since two row matrices cannot be multiplied, psi, phi psi is meaningless. Clear? Now we are repeatedly talking about scalar product. What is the physical significance, physical meaning of this scalar product? You know, the scalar product, it can be interpreted in two ways. Firstly, you know, if you take the analogy of the scalar product of ordinary vectors in the Euclidean space, let's say A dot B, what does it represent? A dot B means component of A along B, or the projection of A on B. This represents the dot product. When a projection of A dot B represents the projection of B on A or projection of A on B. Now the product of phi psi, this is the scalar product of phi psi, it also represents the projection of let us say psi onto phi, similar manner. Second, in the case of normalized state, and according to Born's probabilistic interpretation, normalized state means the scalar product with itself should be 1, and Born probabilistic interpretation we have already talked about. Quantity phi psi, what does it represent? It represents the probability amplitude, that the system state psi will, after a measurement is performed on the system, be found in another state phi. So let us say we have the state in quantum mechanics, after taking the measurement, the state is changed. So phi psi represents, like if you have the state psi, if you take the measurement, after that it will converted and it will be found in another state phi. Is there any question till now? Kartik, Murli, Harry? If no question is there, we can do one last problem. Then we'll wrap up the session. One last problem, and we'll discuss the second part of this mathematical tool in the next class. Let's do it. Acha, let me give you homework, then you will check it out. Consider two states, one is psi 1, another one is ket psi 2. Phi 1, phi 2, phi 3 are orthonormal kets. You know the meaning of orthonormal kets. Phi 1, phi 2, phi 3, phi 4, these are orthonormal ket, means phi I, phi j, this is equals to 0, and phi I equals to 1. This is the meaning of orthonormal, na? Find the value so that psi 1 and psi 2 are orthogonal, means psi 1, psi 2 scalar product of psi and psi 2 is 0. That is the meaning. So whether you calculate psi 2, psi 1 or psi 1, psi 2, whatever you calculate, that should be 0. So you have to find out the value of E. Will you be able to do it at home? Take this as homework. Okay guys, so we are stopping here today. We will discuss the second part in the next session. We will start with operators. It may take another session to complete this mathematical tools, and after that you will be in a good position to understand or tackle problems of quantum mechanics efficiently. Okay, now this topic was a little bit boring, as some of you told, but you have to revise it. Okay, you have to revise it. If you do not understand this class, then it may create problem in the later time. So you must understand whatever we discussed today, and we will be discussing in the next class. Okay, very necessary classes, these two classes. Thank you guys, thank you very much, bye bye, take care.